Hi, in this session we will discuss about the concept of balanced supply and balanced load and the relationship between line and phase values for balanced star connected three-phase system and also the total power of star connected three-phase system and apparent power. So first let us try to understand what is meant by balanced supply and balanced load. If the magnitude of three phases are same and if they are displaced by 120 degree, then we call as balanced supply. That is, if the magnitude of voltage of all the three phases are same and if they are displaced by 120 degree, then it is called as balanced supply. So just we can see here in this example the phase voltages VA, VB and VC. The magnitudes are equal, that is VA is equal to VB is equal to VC, and also they should have a phase displacement of 120 degree with each other. But here in the second case, if each phases having the different magnitudes, that is if VA is not equal to VB and if it is not equal to VC, then they are called as unbalanced supply. And also each of the phase voltages will be having different phase angles. Okay, now what is meant by balanced load? If the impedance in all the three phases are equal in magnitude, then we say such load as balanced load. Let us take an example. If the load of the three-phase system has all the resistive component and if all the resistor values are, let us say, some 1 ohms or 10 ohms, then we call such load as balanced load. Or if R1 is say 1 ohm, R2 is 5 ohm and R2 is 10 ohm, then we call such a load as unbalanced load. Okay, now we will see what is the relationship between line and phase values of balanced star connected three-phase system. Okay, so we will take the line currents as IR, IY and IB, and the line voltages are VRY, VYB and VBR. And also let us take the phase voltages as VR, VY and VB. So we will first define what is mean by line voltage, phase voltage, line current and phase currents. Phase voltage means the voltage across each phase or the voltage between any line and the neutral point is called as the phase voltage. That is, in this example, we have considered a star network. VR is the phase voltage, VB is the phase voltage and VY is the phase voltage, right? So across each phase, whatever the voltage, we call it as phase voltage. That is, each phase means how they are connected. They are connected, one line is connected to the supply or line and the other end is connected to the neutral point. Therefore, the voltage between this point, that is one line and the neutral point, is called as an phase voltage. So here the common point is called as the neutral point and we represent it as N. Okay, so the difference of voltage between this and this point is called as phase voltage. So what is meant by line voltage? The voltage between any two lines. Say for example, if this is the line R and Y and B, so difference between the line R and Y, we call that voltage as line voltage, or the difference between two voltage difference between two lines R and B can be called as the line voltage, or the voltage difference between the line Y and B can be called as another line voltage. So here we have represented the line voltages between R and Y. It is VRY. Between R and B, it is VBR, and between Y and B, VYB. So these three are nothing but the line voltages. I repeat, phase voltage is the voltage between single line and the neutral point, or the voltage across any phase. In this case, VR, VB and VY are nothing but phase voltages, whereas the line voltage is the voltage difference between two lines, In this case, VRY, VBR and VYB are nothing but the line voltages. Now, what is meant by line current? Current flowing through any one line, we call it as line current. So here current flowing through the line R is called as the line current, that is here through this line R, the current IR flows, which is called as line current, and current flowing through the line Y, IY, is called as line current. Current flowing through line B, which is IB, is called as another line current. Now, phase current means the current flowing through any phase. So here current flowing through the phase R or phase B or phase Y are called as phase currents. Okay, now the vector diagram representing the phase and the line voltages we have shown in this figure. This is the phasor diagram representing the line and phase voltages. So how we will write this vector diagram is, first we must take the phase voltages. The phase voltage VR, let us take it as along x-axis, and VB, which is having 120 degree phase shift, and VB leads VR by 120, and VY lags VR by 120. Okay, so in this way, first we will show 120 degree phase shift between VR. Let me just highlight 120 degree phase shift between VR, VY and VB. Now we will extend VR in negative side, which gives the negative value of VR. Similarly for VB and VY. So we will get minus VR, minus VB and minus VY. Okay, so let us continue. In star connected system, there are two windings between each pair of the outer, and due to joining of similar ends together, the EMF induced in them are opposition. That is here each terminal of each phases are connected at a common point. Therefore, we can say the EMF induced in them are in opposition. So we can also represent VR as minus VR in other side. Hence, the potential difference between two lines is called as line voltage, which is the vector difference of phase EMFs of the two phases concerned. Very important point. Potential difference between two lines is called as a line voltage, which is nothing but vector difference of the two corresponding phase EMFs, or a vector difference of phase EMF of the two phases concerned. For example, if we consider the two lines R and Y, then the line voltage, the voltage between R and Y is ERY, which is nothing but the vector difference of the phase voltage of R and phase voltage of or the phase voltage produced by the line Y. Hence, ERY can be represented as vector difference between the two corresponding phase voltages. That is, the line voltage between the two lines is equal to the vector difference between the corresponding phase voltages. Therefore, VRY is equal to VR minus VY. Here VR and VY are phase voltages. We can also represent in vector sum form, that is VRY is equal to VR plus of minus VY. And according to this equation, that is VRY is equal to VR minus VY, we will complete the vector diagram. So VRY is nothing but the resultant vector of VR and minus VY. Therefore, here let me just represent VRY is the resultant of minus VY and VR. Similarly, VYB is the resultant of VY and minus VB, or the line voltage VYB is the vector difference between the two corresponding phase voltages. Two corresponding phase voltages, which phases we are considering? Y and B in this case. So it is VY minus VB. Similarly, the line voltage VBR is the phase vector difference between the two phase voltages, that is VB minus VR. Okay, now let us take the line voltage VRY and we will find the expression. From this parallelogram, what we can write? According to the rules of parallelogram, we can write the resultant vector VRY as square root of VR square plus VY square plus 2 VR VY into the phase angle between R and Y. Okay, so what is the phase angle between this and this point? It is 60 degree. The phase angle between VR and VY is 60 degree, because from the angle between VR and VB is 120 degree and angle between VR and VY is 60 degree. Therefore, VRY can be written as square root of VR square VY square. According to the vector rule, we can write VRY is equal to square root of VR square plus VY square plus 2 times VR VY into cos of 60 degree. Why 60 degree? Because there is an phase shift of 60 degree between VR and VY. Okay, so in a balanced supply, let us assume all the phases having the same magnitude, and let us call the phase voltages as VP. That is, VR, Vy and Vb are equal, and which is equals to Vp. So in this expression, let us replace all the phase voltages as Vp, and cos of 60 is 0.5 or 1 by 2. So simplifying, we will get VRY as root 3 times Vp. What is VRY? Line voltage. Line voltage is equal to root 3 times phase voltage. Similarly, let us take any other two lines, that is between Y and B. The line voltage VYB can be written as the vector difference between the two phase voltages, that is Vy and Vb. And here we can apply the same rules and we will get the expression for VYB as root 3 times Vp. Similarly, when we consider the two phases R and B, the line voltage VRP can be written as Vb minus Vr, and which is equals to root 3 times Vp. And in a balanced star system, all the line voltages will be having the same magnitudes, and therefore let us call them as VL. Therefore, line voltage is equal to root 3 times phase voltage. This is the relationship of line and phase voltages in three-phase star-connected system. And now let us see what is the relationship with the phase and line currents. So in a star-connected system, each line conductors are connected to the separate phase. Therefore, we say same current will be flowing through line and phase. Hence, line current is equal to phase current. I repeat, in a star-connected system, each line conductor is connected to a separate phase. Hence, the same current will be flowing through line and phases. Hence, line current is equal to phase current. So, you can just observe this diagram here. In this diagram, this is a phase. There is no branching over here, which is connected to the line. So, even this phase is connected to separate line. This phase is connected to separate line. Therefore, whatever the line current flows, that is IR, the same thing will be flowing through the phase. Here similarly IY, same thing will be flowing through this phase Y. Similarly for B, the same current will be flowing through the phase B. Hence, line current is equal to phase current. I repeat, in a balanced star-connected three-phase system, line voltage is equal to root 3 times phase voltage and line current is equal to phase current. Now let us see the total power output of the three-phase star-connected system. Each power outcome from each phase, that is the power outcome from each phase, let us call it as Vp Ip into cos phi. In a single phase AC circuit, we know that power is equal to Vi cos phi. So here, considering each phase, we will represent the power output as Vp Ip into cos phi. So when we consider the total power of all the three phases, simply we will multiply the power outcome from each phase into 3. Therefore, 3 times total power outcome of the three-phase system is 3 times Vp Ip cos phi. Here we know the relationship between phase and the line voltages, that is Vp is equal to VL by root 3 and Ip is equal to IL. So we can write expression for P in terms of line quantities as root 3 times VLIL into cos phi. That is, power outcome of the three-phase star-connected system is equal to root 3 times line voltage into line current into power factor, or in terms of phase parameter, you can also represent P is equal to 3 times Vp Ip into cos phi. In terms of line parameter, root 3 times VLIL into cos phi. And the apparent power of the three-phase system is nothing but 3 times apparent power per phase. Apparent power is nothing but a product of RMS value of voltage and RMS value of current. Here we will take the voltage in each phase. Therefore, voltage in each phase is Vp and current is Ip. So multiplying this with 3, we will get the apparent power of three-phase system. That is, apparent power in each phase is Vp into Ip into 3 will gives the total power, apparent power of three-phase system. So again, replacing Vp with VL by root 3 and Ip as IL. So we will represent apparent power as root 3 times VL into IL. That's it. Thank you.